last class we have seen that the cross section of a direct current machine can be drawn somewhat like this. It has a stator core, to which poles are connected, stationary poles, field poles. In general, a DC machine can have more than 2 poles. The poles are fitted with pole shoes, which covers the most of the air gap part. And carries winding. These windings are electrically excited with DC current such that alternate north and south poles are generated. The armature, the rotor carries the armature, is mounted on a shaft, axial shaft. The connection to the rotor are obtained by means of commutators and brush segments. The brushes are normally pressed what we call the interpolar region, that is, it connects to the conductor that are at the interpolar region. This is plus, plus, minus, minus. The brushes divide the armature is a closed winding. The brush divide the armature in several parallel paths. The closed winding of the armature can be schematically represented like this, and the brushes here, the positive brushes are connected together and the negative brushes are also connected together. And two terminals are finally brought out. However, the brushes divide the whole armature winding into a number of parallel paths. Number of parallel paths A is equal to the number of poles of the DC machine for lap winding, and the number of parallel paths A equal to 2 for wave winding. Now, when such an arrangement is rotated inside the stator, this armature is rotated inside the stator, an EMF is induced in the armature coils and across the brushes, as the coils are series connected between brushes, as well as if an current is allowed to flow through these conductors by either connecting an external resistance and rotating the machine, in which case it acts as a generator, or by supplying the armature from an external voltage source, in which case it acts as a motor, a torque is also produced. In this class, we will try to find out the expressions of this generated EMF and the generated torque as functions of different machine parameters. For this purpose, let us take what we call a developed view of this cross section. Developed view is nothing but cutting the cross section diametrically and unfolding it in a straight line. If we do that exercise, along this axis and hold it open, then it will look somewhat like this. Let us say this is my position 0. There are p number of poles. If this is the interpolar region, then the axis of the first north pole will be at a position pi by p. The next interpolar region will come at 2 pi by p. The next pole will come at 3 pi by p. And we will come back to the original position for the next polar region. Interpolar region will be at 4 pi by p. Since a pair of poles, the action due to a pair of poles is identical for all pole pairs, we will concentrate only on the behavior of the machine under one set of pole pairs. So, our diagram ends here. Let us say this is the north pole and this is the south pole. The poles are fitted with pole shoes, which covers most of the armature surface. Therefore, we can draw the pole shoes somewhat like this. So, this is north pole, this is south pole. The flux density waveform produced by the field winding the flux density waveform produced by the field winding can be approximated by a flat top trapezoidal waveform. Which goes to 0 in the at the interpolar region. In this region, flux is going from the pole to the armature, which we call positive flux and denote by these arrows. And this is the negative flux which flows from the armature to the south pole and denoted by these negative arrows. So, this is the flux density waveform due to the field winding alone. Now, consider at any time a coil on the armature, full pitch coil. By that we mean that if one end of that coil is under north pole, the other end will be under south pole. Let this be the position of the coil at time t, and let the armature along with this coil be moving in this direction with a angular velocity of omega m. Then after a short time t plus delta t, this coil will move by an angle delta theta. This angle will be delta theta. What will be delta theta? Delta theta equal to omega m into delta t. Now, let us look at the change in flux linkage of this coil delta lambda. At time t, the flux passing through the coil can be found by integrating the flux density waveform between these two limits, and at time t plus delta t, the flux density waveform flux linkage can be found by integrating the flux density waveform between these two lines. However, let us find out the change in flux linkage, or rather change in flux first, delta phi. The change in flux delta phi, if we try to find out, we see that the flux passing through this area positive flux passing through this area has gone out of the coil, as well as some amount of negative flux has been included, and from the symmetry of the flux density waveform they are equal. how much is the flux contained in this hatched portion? It can be found from the flux density waveform and the area. The area of that, the armature area due to this angle delta theta, delta A, equal to the arc length r into delta theta into the length of the armature. So, delta phi equal to B into delta A, that is delta phi equal to B r L delta theta. So, and 2 times this, and that is in the negative direction. So, this is minus 2 times B r L delta theta, and the change in flux linkage delta lambda equal to number of turns in this coil, let us denote it by N c. So, delta lambda equal to minus 2 N c B r L delta theta. So, the magnitude of the EMF induced in this coil at the instant t is given by E equal to limit delta theta tending to 0 delta lambda by delta t, that is equal to d lambda dt. So, E equal to minus 2 N c B r L d theta dt, that is minus 2 N c B r L omega m. So, we see that the voltage induced in a coil at a given position theta is proportional to the flux density at that position and the rotational speed of the machine. So, we can draw the waveform of the induced voltage in that particular coil as it moves along the armature surface. This is 0, this is pi by p, this is 2 pi by p, this is 3 pi by p, this is 4 pi by p. As the coil moves along this direction, the EMF induced has a similar waveform as that of the flux density waveform, that is where theta is the position of the first end of the coil. Now, this is to be understood that we do not see this waveform on the brush though, since the coils are connected to the brush through commutators. Let us try to visualize the situation. The brushes are placed at the interpolar region. Therefore, this coil will connect to the brush first when it is at position 0 and the induced voltage in the coil is 0. And if this is the only coil, then the commutator segment spans half the armature periphery. Therefore, for half the cycle it will remain connected to one commutator segment, and then for the rest half it will connect to the other commutator segment. Hence, in effect the voltage induced in the brush, voltage at the brush will be the rectified waveform of the voltage induced in the coil. This is the voltage induced, this is the voltage induced in the coil, this is the voltage in the brush, across the brush. This would have been the voltage across the brush had there been only one coil on the armature. But now consider a practical DC machine where there will be a large number of such coils. For example, if we look at the armature surface, this contains slots. And DC machines usually have double layer. So, in each slot there will be 2 coil ends. So, and if we assume that one of these slot width of denote the width of the slot by delta theta, then the number of turns NC in a coil can be represented in terms of delta theta as follows. Let there be total Z conductors in the armature, these are uniformly distributed over the armature periphery. So, and the armature is double layer. So, the Z number of conductor are distributed over a mechanical angle of 4 pi. So, the number there is the number of turns in a coil, that is conductor in a coil, is NC. So, NC can be written as Z divided by 4 pi into delta theta. Hence, the voltage induced in a coil EC equal to minus 2 B R L omega m Z by 4 pi d theta, that is the voltage induced in a single coil. Now, it is to be understood that between two brushes there are number of coils connected in parallel. In fact, all the coils that are in the span 2 pi by a brushes are set apart by an angle of the number of conductors between two opposite polarity brushes is given by 2 pi by A. The number of coils connected in series between two brushes is given by 2 pi by A. Therefore, the induced voltage between the brushes can be written as integral E b in a practical DC machine can be written as integral 0 to, because one of the brush will be at the interpolar region 0, the other will be at 2 pi by p, but the number of coils connected in series between these two brushes will be 2 pi by A, where A is the number of parallel paths. So, 2 pi by A E c d theta E c, which is equal to 2 omega m z by 4 pi integral 0 to 2 pi by A b r L d theta. Now, let us do a change of variable as follows. Let us define phi equal to A by p theta. Therefore, d phi equal to A by p d theta. So, E b can be written as 2 omega m z by 4 pi into p by A integral 0 to 2 pi by p b r L d phi. This term under integration can be easily identified as the total flux passing through the north pole. Hence, this is termed the flux per pole or phi p. Therefore, the simple formula of induced voltage across two brushes is given by So, this is also the terminal voltage of the DC machine or the generated back EMF in the DC machine, because the voltage is measured across the brushes. So, the back EMF expression is given by E b equal to Z divided by 2 pi p by A phi p omega m. This is sometimes written as k phi p omega m, where k is the back EMF constant as given by k equal to Z by 2 pi p by A. Now, A equal to P for lap winding and A equal to 2 for wave winding. there is a slightly different formula for this EB also. So, if we write omega m in terms of RPM, then omega m equal to 2 pi into n, where n is the rotational speed of the DC machine rotor in RPS, or equal to 2 pi n by 60, where the rotational capital N is the rotational speed in RPM. So, EB can be written as phi p z by phi p z n by 60 into p by a. This formula is also very much in use. So, we have seen that how to find out the induced EMF in a DC machine from the first principle. Now, let us find out the torque. For that, we again go back to the original diagram of the developed diagram. The flux density waveform due to field winding we have mentioned is trapezoidal, that is of this shape. And the armature contains slots and coils in the slots in double layer. We have seen that if this armature is moving at a speed omega m, in this direction, then there will be a induced voltage in these coils. What will be the direction of the induced voltage? From Faraday's principle, we can say that the induced EMF will be in such a direction that if a current is allowed to flow in the coils, it will oppose the change of flux linkage. Now, we have seen that due to the motion, the flux linkage change is in the negative direction, that is positive flux linkage tends to decrease. So, the current will flow in this coil in such a fashion that this decrease in the flux linkage is compensated, that is the currents in these coils will produce positive flux in this direction. So, what will be the direction of current flow? It has to be understood that the positive flux means flux flowing from the field to the armature. Definitely then the current flowing in these coils will be of dot polarity, and current the other side of the brush will have cross polarity due to the induced EMF. Now, we also know that if there is a current carrying conductor under a magnetic field, then the conductors experience a force, and from the Fleming's left hand rule we can find out the direction of the force. In this case, the direction of the force will be opposite to motion. We can also find out the magnitude of this force acting on some conductors. Let us say one coil, delta F will be equal to the number of conductors at any given position, which due to double layer winding is 2 N c. So, this will be 2 N c, and then B into L and into I c, that is the current flowing through those conductors. Now, if the armature has a number of parallel paths, then I c equal to armature current I a by A. Therefore, delta F equal to 2 N c B L I a by A. Now, let us look at the original diagram of the DC machine. The conductors here are experience a force of delta F in the direction opposite to the motion. Similarly, the conductors diametrically opposite are also experiencing a force, and again in the direction opposite to the motion. So, the torque produced by these conductor sets, these two sets of conductor, is given by delta T equal to 2 into R into delta F equal to 4 N c B R L I a by A. However, we have found out N c equal to Z by 4 pi into d theta. So, dt equal to Z by pi B R L I a by A into d theta. Now, we know that the total torque, in order to find the total torque, we will have to add the torque produced by individual coils between two brush, because the rest of the coils will now be taken care of by other sets of coils. So, there are between two brushes, we will have to integrate them. So, torque T equal to Z by pi into I by I A by A. We have to integrate over one pole pitch, that is integral 0 to 2 pi by P B R L d theta. However, there are P by 2 such pole pairs which is generating the torque. This is the torque produced by one pole pair. So, the total torque, for in order to get total torque, this has to be multiplied by P by 2. So, the total torque expression will, this we again identify as flux per pole. So, this will be Z phi P P by 2 pi A I A equal to Z by 2 pi into P by A into phi P into I A. This is again can be written as K phi P I A, where K is the torque constant, and we found that the torque constant is same as the back EMF constant found during calculation of the induced EMF. This can also be shown from the power balance. Let us say this is the armature with the brushes, with an external resistance connected and being rotated in the direction the speed of omega m. Let the current here be I A. If we assume no loss in the machine, that is, if we assume armature resistance of the machine to be 0, then the power produced by the generator equal to E B into I A, but E B equal to K phi P omega m I A. The electrical power produced must be equal to the mechanical power input. So, in order to rotate this armature, some amount of mechanical work has to be done, that is, it has to be rotated against a generated torque T E. Therefore, T E omega m should be equal to P E equal to K phi P omega m I A, or T E equal to K phi P I A, which is same as what we have obtained for as the torque expression from the first principle. This we have shown when the machine works as a generator. However, the same conclusion will be arrived if we consider a motor mode of operation. In the motor mode of operation, the only change will be the direction. The armature terminals will be connected to an external source of voltage V, and if we neglect the armature resistance, then in steady state V equal to E B equal to K phi P omega m. Therefore, electrical power input to the machine is V I A equal to K phi P omega m I A. This must be same as the mechanical work done. The direction of torque will also now change, because the direction of current has changed. So, T E omega m should be equal to K phi P omega m I A, or torque in the motor mode will also be given by K phi P I A. Therefore, we have seen that in a DC machine, when the armature rotates under the influence of field poles, field flux, a EMF is induced across the brushes. The magnitude of the EMF is proportional to the flux produced by the field poles, that is flux per pole phi p, and the rotational speed of the armature. In the same manner, we have shown that if a current is allowed to flow in the armature conductors, either by connecting a load in the generating mode or by connecting the armature to a separate voltage source to make it run as a motor, then an electromagnetic torque is generated, the magnitude of which is again proportional to the flux per pole and the armature current in the armature circuit. For the motoring mode, the current is injected into the armature by an external circuit, so that electrical power is input to the machine, and hence the generated electromagnetic torque will be in a direction which will assist motion, that is mechanical work will be done. So, the direction of electromagnetic torque will be in the same direction as that of rotation, that it will assist rotation, and hence electrical power input will be converted to mechanical power output. The reverse will happen in the generating mode, that is, if a load is connected, then the current flowing through the armature winding will try to stop the motor, that is, the electromagnetic torque produced will be in a direction which is opposite to the direction of rotation. However, if the flux per pole and the magnitude of the armature currents are same in the motoring and in the generating mode, then the magnitude of electrical torque produced will be given by the same formula, that is K phi p I A, both in motoring and in generating mode. Similarly, the induced voltage either in the motoring mode or in the generating mode will be given by the formula K phi p omega m. So, whether the machine operates as a motor or as a generator, the formula for Induced voltage in a DC machine is given by EB equal to K phi p omega m, where K equal to Z by 2 pi p by A. Z is the total number of armature conductor, P is the number of poles and A is the parallel path, and electromagnetic torque is given by K phi p I A, where K has the same expression. Thank you.